For most of the history of spaceflight, rockets were used only once. Every launch meant building a highly complex machine with precise engines, lightweight structures, and advanced guidance systems, and using it for a single mission. After reaching space, the rocket fell back to Earth and was completely destroyed. This wasn't a technical limitation. It was an economic problem. Spaceflight was extremely expensive because the most valuable part of every mission was thrown away. SpaceX changed that idea. Instead of building rockets designed for one-time use, SpaceX focused on building rockets that could return and fly again. This approach doesn't just reduce cost, it changes the entire way rockets are engineered. In the past, rockets were designed as expendable vehicles. The first stage of a rocket provides about 90% of the total energy needed to reach orbit. This stage includes the largest amount of fuel, the main engines, the guidance systems, the main structure. After separation, the first stage fell back to the planet without control and burned up in the atmosphere. Yet this part represented around 70% of the total launch cost. Even the space shuttle, which was technically reusable, did not solve this problem. Repairing the shuttle, replacing tiles, overhauling boosters, and preparing it for the next mission, was extremely expensive. So, it wasn't true operational reuse. In earlier decades, NASA studied fully reusable rockets and estimated that reusability could reduce cost by 10 to 20 times. But the required technology did not exist at the time. SpaceX came into the industry with a simple principle: build the minimum rocket needed to reach orbit, and use all remaining capacity to bring it back. To achieve this goal, several engineering requirements had to be met: engines that can restart multiple times, precise control during re-entry, very lightweight and strong structures. To move fast, SpaceX designs and produces almost everything in-house, including engines, fuel tanks, avionics, flight computers, ground systems. This allowed SpaceX to rapidly improve designs and build new versions quickly. Falcon 9's Merlin engines use liquid oxygen and kerosene. This type of engine is simpler, cheaper to manufacture, and can restart several times during a mission. These features are essential for landing the first stage. Merlin engines can throttle down to about 40% of their maximum thrust. This makes it possible to perform a precise landing burn, slowing the rocket down just before it reaches the landing pad. A timing error of only 1/10 of a second can cause the landing to fail. After stage separation, the Falcon 9 flips around and uses titanium grid fins to control itself in the atmosphere. These fins let the rocket fly in a stable path and steer toward the landing site with high accuracy. Older rockets had no ability to steer during this phase, they simply fell like debris. Lightweight structure. The body of Falcon 9 is made from aluminum-lithium alloy, which is extremely strong and lightweight. Every kilogram saved in structure can be used for more fuel, which is what makes landing possible. Landing a tall, heavy rocket on a small landing pad is not controlled by GPS alone. Falcon 9 uses a combination of inertial sensors, GPS data, radar altitude measurements, airflow control using fins, computer flight control, engine gimbal, thrust vectoring. These systems work together in real time, adjusting the rocket's path in milliseconds. The result of these innovations is a major transformation in space economics. A Falcon 9 launch costs around $50 to $70 million. When the first stage is reused several times, the real cost per flight becomes much lower. In comparison, traditional rockets such as the Delta IV Heavy cost $350 to $450 million per launch, and the entire rocket was destroyed. SpaceX did not reduce cost by buying cheaper parts. It reduced cost by reusing the most expensive parts. This is similar to aviation. If airplanes were used only once, a ticket would cost millions of dollars. With reusable rockets, SpaceX built Starlink, a network of thousands of small satellites providing global internet coverage. Launching this many satellites would have been financially impossible with expendable rockets. SpaceX also developed Crew Dragon, a spacecraft that can carry astronauts to the International Space Station. For the first time, a private company is sending humans into orbit. Falcon 9 was only the beginning. SpaceX is now building Starship, the largest rocket ever constructed. In Starship, both stages are designed to be fully reusable. The rocket is made from stainless steel, which stays strong at very low and very high temperatures. Starship uses a new engine called Raptor, powered by liquid methane and liquid oxygen. Methane can be produced on Mars using local resources. This means Starship is designed for interplanetary missions. If Starship succeeds, the cost of reaching orbit could fall by another factor of 10, unlocking missions to the Moon. Building bases on Mars. Construction of structures in Earth orbit. Global, low-latency communication. Deep space science missions. In less than 20 years, SpaceX has changed the space industry. Rockets can land and fly again. Precision landing is now routine. Launch costs have dropped dramatically. Private companies now send humans to space. True reusability is not just a slogan. It is a fundamental shift in how rockets are designed and operated. SpaceX has taken a major step toward a multi-planet future for humanity. Thank you for watching. To watch our upcoming videos, please subscribe and hit the bell icon to be notified as soon as new videos are uploaded.